Bayes' theorem is a rule for updating probabilities when new information arrives. It answers a very specific problem. We often know how likely some evidence is if a hypothesis were true, but what we actually want is how likely the hypothesis is given that evidence. Those are not the same thing, and mixing them up leads to serious mistakes. Start with conditional probability. P of A given B means the probability that A is true, assuming B has happened. P of B given A means the probability that B happens, assuming A is true. These sound similar, but they answer opposite questions. The order matters. Here is the core idea, without math. You begin with a prior belief about a hypothesis. You then see evidence. You ask how well that hypothesis would predict the evidence you just saw. You increase or decrease your belief accordingly, and then rescale so all probabilities add up to 1. That is Bayes' theorem. Now the formula. For events A and B, Bayes' theorem says P of A given B equals P of B given A times P of A, divided by P of B. Read it left to right. The posterior, what you believe after seeing the evidence, equals the likelihood, how expected the evidence was under the hypothesis, times the prior, what you believed before, divided by the overall probability of seeing that evidence at all. That denominator, P of B, is crucial. It represents all the ways the evidence could have occurred. If there are two possibilities, A and not A, then P of B equals P of B given A times P of A, plus P of B given not A times P of not A. This is where competing explanations are weighed against each other. Bayes' theorem is not magic. It comes directly from the definition of conditional probability. P of A given B is the probability of A and B happening together, divided by the probability of B. P of B given A is the same joint probability divided by the probability of A. Rearranging those definitions gives Bayes' theorem exactly. A numerical example makes this concrete. Suppose a disease affects 1 in 1,000 people. A test correctly detects the disease 99% of the time and falsely flags healthy people 1% of the time. You test positive. What is the probability you actually have the disease? The prior probability of disease is 0.001. The likelihood of a positive test if you have the disease is 0.99. First, compute the overall probability of a positive test. That is 0.99 times 0.001 plus 0.01 times 0.999. This equals 0.01098. Now apply Bayes' theorem. The posterior probability of disease given a positive test is 0.99 times 0.001 divided by 0.01098. That is about 0.09 or 9%. This result surprises people because they ignore the base rate. Even strong evidence can be overwhelmed when the hypothesis is very rare. Bayes' theorem can also be written in odds form. Posterior odds equal prior odds multiplied by the likelihood ratio. Evidence does not create belief from nothing. It tilts existing belief. The biggest mistakes are confusing P of A given B with P of B given A, ignoring base rates, and forgetting to account for all ways the evidence could occur. One sentence summary. Bayes' theorem is the rule that tells you how to rationally update what you believe when new evidence arrives, by combining your prior belief with how well that belief explains the evidence.